Good morning, everyone. Good morning. So, what I want to do for today's lecture is I'll be taking a problem on plane stress. We'll be drawing Mohr circle, drawing out the different orientations, and I have one request. I want to complete the problem today. So, if you have any questions, I'm going to save time at the end of the lecture, okay, so that you can ask me questions. And I'll make sure that whatever I'm doing, I'm clearly writing out the procedure for doing what I'm doing. Okay? All right. So you have the problem on your pre-lecture slides, which have been posted on Carbon under the note and the PDF format. So you can take a look at it. So here is a problem. So we have a given plane state of stress. X-axis, Y-axis, okay, and then the plane state of stress has the following stresses acting on this body, on this plane. The shear stress is 80 megapascals. The normal stress, they are all compressive, as you can see. Okay, this is the normal stress here. Normal stress. These are all the normal stresses. They are all compressive. The one along the x-axis is given to us as 150 megapascals. The one along the y-axis is given to us as 30 megapascals. And we want to do the full works on this problem. We want to draw the Mohr circle. We want to find the principal stresses. We want to find the maximum in-plane shear stress. I want to find the strain at this point. I want to find the principal strains, the maximum in-plane shear strain. I want to do everything on this problem. Okay? We'll do this step by step. First step is you always compare this with the given sign convention. X-axis, Y-axis. The given sign convention is that all tensile stresses are positive. So sigma Y, 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 sigma X, X. Those are positive if they are drawn in the following manner. And then if I look at the shear stress, once again, I want to very carefully mention the positive sign convention for shear stress. Consider this face. Look at the area normal on this face. The area normal on this particular face is pointing in the positive x-axis direction, which means that the shear stress is going to be pointing along the positive y-axis on that particular face. Okay, so it's going to be drawn this way. And then once you have one of them, you have the rest of them. So it's going to be pointing down here, to the right, to the left. So this is your positive tau. And based upon the comparisons between the given problem, so this is the problem given, and here is a sign convention. You can obviously see that all these stresses have been flipped. So sigma xx is minus 150, sigma yy is minus 30, and tau xy is going to be minus 80. So compare. I've wantonly chosen this particular example here. Sigma xx is minus 150, sigma yy is minus 30, and then tau xy is minus 80. Okay. Once we have this, then we start off to draw the Mohr circle. We set up the origin, we set up the center of the circle, which is not necessarily the origin of the coordinate frame, and then we have the radius. Okay? So first of all, the Mohr circle axis, positive, sigma, positive tau. The origin is O. So O, 0 and 0 megapascals. Okay? Then we choose the side of interest for us. Typically, the side of interest is always the side on which the axes are going to be labeled. So in this case, I can either choose this or that to draw the Mohr circle. Don't worry about choosing this. We typically go with the right side. Okay? Always. So this is my interest. Which means that I write the center of the Mohr circle as C. It is defined as the average stress, so sigma xx plus yy divided by 2 and 0, because it's sitting on the x-axis or the sigma axis, so there is no tau value for the center. Sigma xx is 150 negative, sigma yy is minus 30, so that's minus 180 by 2 or minus 90. Okay? Then the point A, which is coming from the side of interest. This is sigma xx and tau xy. Which is minus 150 because we are opposite to the sign convention. And then tau xy is minus 80. And so this is coming from the interest. Once again, this is a graphical technique. The foundational equations are similar to what we looked at. We looked at a very simplistic model of just pure tension and pure torsion. Those are the foundational equations. It's not worth our time going and generalizing it because all of these things have to be generalized into 3 dimensions. But to get an idea of what's going on in a given 2-dimensional plane, the graphical representation of Otto Mohr is a very nice way of visualizing things. Okay? Alright. Radius is the distance between the point C and the point A. So radius R is the segment length CA. So this is the following. It's the coordinates of A minus the coordinates of C. Once again, we've seen this before. Sigma xx minus xx whole square. Then I have tau xy minus 0 whole square. All of this, please notice, all of this square root, right? So I typically write it as 1 by 2. Okay? Sometimes the book will simplify this and then say that sigma xx minus this quantity here is sigma xx minus sigma yy divided by 2. Okay, but these are just numbers that we're dealing with, so this is sufficient for us. If you do the substitution, or is sigma xx is minus 150 minus sigma xx plus sigma yy by 2 is nothing but the center point, so that's minus 90 whole square, and then tau xy is minus 80 and 0 all to the power 1 by 2 minus 150 minus 90 becomes minus 150 plus 90, which is 60 square. Then I have 80 square. 60 square and 80 square is 100 square. Square root of that is 100. So it's a good problem. Nice clean numbers. 100 megapascals. So these are the elementary operations. Given the plane state of stress, calculate all of these creatures. Then we have to draw the circle, the actual circle itself. Okay, so let's do that. Point C is a point on the left half plane of the sigma tau plane. Okay, it's on the left half. So let's say here is point C. Minus 90 and then 0. And then I have point A, which is going to be where? Look at point A. Minus 150, so it's obviously on the left half. Is it on the top or the bottom? The positive tau axis is on the bottom because of the fact that this is the way the equations will align with the theory if you use motion. Okay? So which means that I'm going to be sitting on the second quadrant for the point A. Okay, so it's going to be minus 150 and then minus 80. So somewhere here. This is point A. You can mark it and just get a little corrupted. The figure might get a little corrupted, so I'm not going to mark it, but this is point A, this is point C. Draw a line. This is going to be the radius of the circle. Using that as a radius, draw a circle. Okay, so this is approximately a circle. And so here you have Mohr circle. All right. So this is the radius R. Okay. Then what you do is you draw a vertical line passing through the points. There are 4 points of interest, which is the points intersecting the x-axis. So this is 1 point. This is another point. Those are 2 points of interest. And then I have, let's say, point here. And then point there. Let me call them by some Latin letters. So I have A, C, let's say B. I haven't used B anywhere, so B. Then let's call this as D. Let's call this as E. And F. Okay, so these are my points of interest. Now watch this carefully. The distance from the origin to the point B is one stress value. Okay, the distance from here to there. This is one stress value. I'm not going to give it a name yet. The distance from point O all the way to this point F is another stress value, which is along the horizontal direction. We typically call them as the principal stresses, sigma 1 and sigma 2. Sigma 1 on the plane state of stress, sigma 1 is typically called to be greater than sigma 2. Okay, so plane state of stress. sigma 1 should be greater than sigma 2. If you're doing it in 3 dimensions, you're going to have a third principal stress which is going to be 0, because if you're doing a plane state of stress and projecting into 3 dimensions, where is the third stress? It's not there. Okay? So in that case, you will call them a sigma 1, 2, and 3. We are not going to go there. Okay? So here sigma 1 is obviously going to be the greater of the two values, which is, as you can see, this positive value. Not the magnitude, the signed quantity. Okay, so in this case, what is the value of sigma 1? I have the total radius from point C to point B, and then this is going to be the distance from O to C. So that's going to be 10 megapascals, right? 90 minus 100. Is that obvious to everybody, or would you want me to do the calculations for sigma 1? Is that okay with everybody? I just write the numerical value. Okay? So this is sigma 1, which is equal to 10 megapascals, which is essentially, as I can write it out, is the distance from BC, distance from B to C, and then minus the distance from O to C. Okay, so which is 100 minus 90. These are all magnitudes. When we talk about a distance, it's a magnitude quantity. Okay, so this is sigma 1, which is 10 megapascals. So the lesser of the two, notice the magnitude of sigma 2 is larger than sigma 1, which means that that is the more deadlier of the two stresses. But that will come only later on when we talk about failure theories. For the time being, just go with the flow. Whichever is the most negative value or the smaller of the two values, the signed value, that's going to be sigma 2. Sigma 2 is going to be the distance from O to F. I'm going to write it here. It's the distance from O to F, which is going to be the distance from C to F, and then the distance from O to C. This is the magnitude of sigma 2. C to F plus O to C. This is the magnitude, but sigma is on the left half plane, so it has to have a negative value. CF is a radius, which is equal to 100 megapascals. Distance from O to C is 90 megapascals. So 100 plus 90, 190 megapascals negative. And this is sigma 2. And here is sigma 1. Maybe I'll give a brief pause here and see if there are any questions. Yes?
So I was watching a video, and then they gave the formula to find the stresses as just sigma average plus R, and for sigma 2, sigma average minus R.
Your choice to use it. I would always go with the figure, because that is more of an understanding, right? It says that, okay, this is just a distance. All I need to do is calculate that value there.
Yeah, and it's just, it considers the distance between the origin to the principal stress and just adds the radius to it.
You can do it that way.
And if we're on the exam drawing the Mohr circle, let's say it doesn't cross the y-axis, so it doesn't reach the origin. So like I didn't, for example, didn't draw according to scale. Would we lose points for that, or would that be sufficient?
So, for example, you're saying that this is the problem that you're solving in the exam, but then this point is sitting there.
Yeah,
That will be wrong. Absolutely. Because you can visualize that the sigma 1 value, as you said, you can think of sigma 1. Obviously, the distance from O to C is lesser than the radius, isn't it? Which means that there has to be a part of the circle that's going to extend onto the positive side. So that's one way of thinking about it.
Okay.
Right, absolutely. So it's a good point. How do I know that this is crossing the positive x-axis? Distance from O to C is 90 megapascals. Radius is 100 megapascals. So obviously the circle is going to spill over onto the positive axis. Good point.
So it would always cross, it has to cross part of the axis?
Not necessary.
Okay. Just in that case?
It's just in this situation. I mean, I could have like OC being a very large negative value, and then my radius is even more negative, right? So it need not cross it. Okay. So So once we are done with this, we can calculate your tau max in plane values. So those are going to be your points of intersection with the top portions or the bottom portion of this Mohr circle. So that's tau max. Okay, so that's the tau max value. Positive or negative, you write the magnitude first. Okay, so this is tau max. I have to draw it out here. Okay, so this is tau max in plane. All right. The question is, how do I draw the orientations? And tau max, you can see, is essentially going to be sigma 1 minus sigma 2 divided by 2. Okay, or 80 megapascals in this particular case. So tau max in plane, sigma 1 minus sigma 2 divided by 2. Okay, so that's going to be 10 megapascals minus 190 and divided by 2. Okay, magnitude 80 megapascals. Push this up. Okay, maybe I'll pull it down before pushing. Okay, all of you good to go? The thing I'm most interested in drawing is the orientation of these shear planes. Okay, the principal stress planes and then the shear planes. Let's start off with the shear plane. I'm going to draw the Mohr circle here one more time, very quickly. Okay, so this is approximately the circle that we have. Here is the origin. Point C. Pointing. Okay? Alright. To draw the shear plane, should I go counterclockwise or clockwise? Let us start off by going counterclockwise. Okay, so I go from CA all the way to the first maximum shear stress value that I reach, which is right here. This angle I'm going to call it as 2 theta S1. And obviously this is going to be 90 degrees plus this angle here, which I'm going to call as theta. Okay? So I have to calculate theta, which we have done in the previous cases. This is C, this is A, this is the radius, this is theta. Distance from point O to point A, vertically up, E is going to be your shear stress value, which was 80 megapascals magnitude. So this was magnitude of tau xy. So theta is going to be sine inverse of magnitude of tau xy divided by r. Or sine theta is tau xy divided by r. And if I find the answer theta, I'm going to get the following. It's 53.1 degrees. Okay, so theta 53.1. If this is 53.1, then I'm going to mark this angle here as 90 minus theta, which is 36.9 degrees. And I'm going to use that value as well. Okay, so bear with me. So first time I'm going to go from CA counterclockwise to the first shear stress value that I reach. Okay, counterclockwise. 2 theta S1 is going to be whatever the theta is plus 90 degrees. So 2 is theta plus 90. So that's 143.1 degrees. And theta S1 can be found out. 72 point something. 71.6 degrees. Okay. Draw the orientation of the shear directions with respect to the x and the y coordinates. So start with the x and the y. positive x, positive y, which is what is given in the problem. Then with respect to the positive x direction, I am rotating counterclockwise, so I go by 71.6 degrees counterclockwise. I'm going to call these as x suffix s. Okay? My y suffix s is always going to go counterclockwise from my x-axis 90 degrees from there. Right, so this is 90 degrees there. Now I'm going to draw the state of stress by assuming the xs and the ys as the direction that is rotating the plane state of stress. Okay, so here's my plane. xs, ys. The rotation is with respect to the positive x-axis, so if you want, you can draw it out. This is theta s1. Notice where you are going with the 2 theta s1 angle. Am I going to the positive shear stress maximum value or the negative shear stress maximum value? I'm going to the positive value, right? Because this is on the positive direction of tau. So this is plus tau plus sigma, which means that on the face that I'm interested in, which is always where the x-axis is pointing out, the direction of the shear stress has to follow the sign convention. Since I'm going to the maximum in-plane shear stress and that is positive, as I'm going counterclockwise, this guy is going to be directed in this particular manner. Does this make sense to everybody? I'm following the sign convention. Okay? I'm going to the positive maximum in-plane shear stress value, which means that the arrow has to be coincident with what the sign convention for shear stress is. If I find one of these culprits, I find the rest of them. This way, this way, this way. So this is my tau max value. But on the plane containing tau max, I'm going to have an average normal stress value. This is going to be the same in all the directions. Sigma average is sigma xx plus sigma yy divided by 2, where sigma xx is minus 150, sigma yy is minus 30, and so this is obviously going to be minus 90, which is coincident with the x value of point C. So that's going to be minus 90. Which means that on your element, you're going to be drawing it as a compressive stress on all sides. Okay. Makes sense to everybody? Now, I'm going to push this a little further up. Is casting a dark shadow on our proceedings. I think I was that culprit who made the talkboard get stuck there. Now somebody will come and tell you, hey, what is so special about going counterclockwise? Why not go clockwise? Why not? Right? Let's try that. So rather than go counterclockwise from AC, I'm going to go clockwise. So look at this. I'm going to call this angle as some 2 theta prime, which is equal to 36.9 degrees. So theta prime is half of that, 18 point something. Theta prime is that divided by 2, so 18.5 approximately. I mark my positive x and y directions, and this is clockwise. This is important. This is counterclockwise from CA. Please notice that this is counterclockwise, that is clockwise. I mark my x and y directions. Now I'm going to go clockwise with respect to the x-axis by an amount theta prime, which is 18.5 degrees. So clockwise. Let me call that as the x prime direction, 18.5 degrees. Where's the y prime direction? From x prime, I rotate 90 degrees to draw my y prime. Does this make sense to everybody? Notice that as I'm going clockwise from the line CA out to the maximum shear stress value here, the maximum in-plane shear stress value here, I'm going to the negative value. Okay? So here I was going to the positive tau max in plane. This is negative tau max in plane, which means that if I draw the element now, the plane element, x prime, y prime, what do you think is going to be the situation? Since I'm going to the negative tau, look at this guy, which is your culprit. On that side, what should be the direction of the shear stress? It should be opposite to the sign convention, because I am going to the negative value. Once I have one of these guys, that is done, that is done, that is done. I'm going to have an average shear stress max, normal stress value, so this is tau max in plane. I'm going to have an average normal stress value which is compressive, that does not change. Does this look any different from the one I drew before? So there is nothing special about going clockwise or counterclockwise. Whichever way you go, on the plane of failure, if this is the plane of failure, the state of stress will always be the same. Does not matter how your point of view is. Okay? So which is what I'm saying, just be consistent. If you're going to go counterclockwise, just keep going counterclockwise all the time. You have a question? Stretching. All right. I want to take a pause here and see if there are any questions. Yes, sir.
So I'm having trouble understanding why tau max is sigma 1 minus sigma 2 over 2. Is that just kind of how it is, or is there an explanation for that?
It's sigma 1 minus sigma 2. So is that right? That's 10 plus 92. No, that's not right. That's not right. That's not right. Yeah. It's this value here. Right?
So is it just is it the same as r?
It is the same as the radius.
Oh, okay.
That makes sense. So sigma 1 plus sigma 2 by 2 if you take the magnitude of it. And the problem is one has to arrange these in the order sigma 1, sigma 2 and sigma 3 and then do it. But we don't have sigma 3. Sigma 3 is 0. Right? So let me make a correction there. Radius. Now, hang on.
I think it's right. Because it should be
Sigma 1
10
minus sigma 2.
megapascals
So 10.
minus negative 190,
it's-
which is 200.
Oh, yeah.
That's right.
Right. It's not 80, isn't it? It's
Yeah.
100. Yeah, that's my mistake. So I shouldn't have written as 80 somewhere.
I don't think you wrote it down.
Where did I write it? as 80
You
somewhere?
just
You
said it, I don't
said
know.
80, but you
I said 80. No.
You
It's
didn't.
a radius, so that's 100. Yeah, that's right. Yeah. I was thinking 190 minus 10, 180 by 2. That's also not right. So this is fine. This is fine. But you don't need to go by the formula. This is just the radius up. Don't you need to go by the formula. Thank you. Okay. All right. Are there any questions on this? Everybody good to go? Yes.
Could you explain again how you found the direction of tau max?
Okay. Yeah. So let's say that I'm going counterclockwise. Yeah. So I'm going from the line AC to the positive tau max value, right? So which means that I first draw this xs and ys, which is okay, right? I come to the side that I'm interested in, which is always the side where my x-axis that I've drawn is pointing out. I'm going to the positive tau max value, which means that it has to follow the sign convention. The sign convention dictates that if I look at the area normal on this side, it's pointing along the positive x direction, which means that the shear stress has to be along the positive line. I'm doing the opposite on the other. Yes, sir.
So that's regarding the ones that are going like that, which are going to go counterclockwise. But then what about the ones on the top? Wouldn't they be the opposite to make it go counterclockwise?
What do you mean?
Like the tau maxing plane that's going like that on the top and the one that's going like that on the bottom.
This one and that one?
Yeah.
They have to counter the couple caused by these two. So this one, if I look at this one, there has to be an equal and opposite one on the back. They are causing a couple which is clockwise.
Yeah.
To counteract that, I need to have equal and opposite on the top and the bottom, which will cause a counterclockwise. This was the same thing that we did when we drew volume elements. Instead of drawing it as a volume element, you're just drawing it as a flat surface. Yes?
Alright, so you drew the 2 theta S1 there. What would 2 theta S2 be in that?
2 theta S2 would be all the way from here to there.
Okay, so then is it always, whichever one you get to first, that's always going to be 2 theta S1? Okay.
Yes.
For problems like this, like actually theoretically, do you have the freedom to go ahead and move your axis?
Move my axis, you mean this point?
Yeah, do you have, or is that initial?
I mean, you got to start off with an origin. You got to start off with a coordinate origin. And typically, if you're using Mohr circle, this is the convention: is that if you have positive sigma here and positive tau there, then the answers that you get. Can you please explain later? If you're going to use Mohr circle, you have to be wedded to the fact that this is positive sigma and positive tau. That cannot be changed.
Yeah, I'm sorry, I said axis, I meant origin. Like, do you have the freedom to move it?
You could. I mean, you would have to do a change of axes. I mean, I can have a new set of axes which I start from here called sigma prime and tau prime. Is that what you're talking about?
Yeah, that.
Yeah, you'll have to do a coordinate transformation. So which means everything will have to be shifted by 10 megapascals. But it's not worth the effort, right? Because you already know that your origin is sitting here. So you can do it, obviously. All right. Principal stresses. I want to get to it. We have 15 more minutes left. So let's do the same thing for principal stresses as well, and then I'll write out the strain equations. I'm going to get rid of this figure here, because I'm going to do the same thing for principal stresses. Let me go clockwise, let me go counterclockwise, let me do cartwheels, let's see what happens. Okay? Right. Once again, positive sigma, positive tau. I have my origin, I have a Mohr circle from before. Point C, point A, CA is my reference line, sigma 1, sigma 2. Do I go to sigma 1 first or do I go to sigma 2 first? Let us go to sigma 1 first. All the way from CA counterclockwise. This is going to be 2 theta P1. And what I want you to take home is that this axis system is obviously not the same as x prime and y prime, which means that the axis system are for your convenience. That should not have a bearing on what the physical effect of the stress is on the body. The physical effect of the stress is going to be the same no matter how you're going to be drawing your axis system, no matter how you're going to be consistently selecting your axis system, as long as you're consistent. Okay? So that's going to be the same case with principal stresses as well. So let's take a look at it. 2 theta P1. That's going to be 180 plus the theta angle. So 2 theta P1, 180 plus 53.1. We had calculated theta as 53.1 a couple of minutes back. You see CCW from CA. I'm going to sigma 1. So theta P1 is obviously going to be an obtuse angle. So that's 114 something, 160.6 degrees. Okay. Now I draw my axes. Start off with x and y. 116 degrees counterclockwise, because I'm going counterclockwise from the line CA all the way to sigma 1. So I'm going to be somewhere here. I'm going to call this as my 1 axis. Perpendicular to that, counterclockwise, is my 2 axis. Right, I'm going counterclockwise once again. I draw my element, which is aligned with the xy direction in the following sense. Right, so now I'm going to have my 1 direction, 2 direction, this angle here is the 116 degrees, theta P1. On the 1 axis, what am I going to have? I'm going to have tensile stresses 10 megapascals. This is sigma 1. Sigma 1. On the 2 axis, I'm going to be going to sigma 2, which means that I'm going to have compressive stresses, which is now whatever, minus 190 or something. So that's sigma 2. Sigma 2. And by the mathematical nature in which the principal stresses are defined, there will be no shear stresses on this plane. When you find principal stresses, if you're using the math behind the mechanics here, if you're finding principal stresses, you're trying to find the plane that contains the maximum normal stress. And such planes will eventually become free of any shear stress. Okay, so we did not go through the math. We saw it in one brief instance when we looked at failure of a brittle material under torsion. Okay, but there is a deeper eigenvalue problem that one has